Hi everybody. My name is Mate, and today I'm going to be discussing an issue that I hope you're all well aware of, and that is the issue of global warming. This presentation is a part of my IB diploma, and more precisely CAS. CAS stands for Creativity, Action and Service, and this presentation is going to be my CAS project, a very important part of CAS, so I hope you enjoy the topic presented. So, back to the main theme, global warming. Global warming is an important issue in today's world more than it ever has been in the past. It seems that every year there are more and more media reports of a pending doom coming from the rise of carbon dioxide levels in the atmosphere, increasingly intensive agricultural farming, and the use of CFCs. For my presentation, I won't just be talking about the ethics behind global warming, but also teaching you a little bit about the chemistry and physics behind global warming as an aspect of what I have learned in the International Baccalaureate. For chemistry, I'll be considering some of the simple reactions that can occur in the atmosphere between CFCs and ozone, as well as an understanding of the various different substances that can cause global warming, not just carbon dioxide. For the part of the presentation involving physics, I'll be talking about how the frequency and wavelength of greenhouse gases can cause them to get trapped in the atmosphere and therefore allow for the greenhouse effect to occur. I'll also talk about the effectiveness of different energy sources and energy loss. With this presentation, I hope that you can just gain a bit of a better understanding in the fields of physics and chemistry, but I will say before I start that a good understanding of these fields beforehand will be required to understand the theory behind the subject. I'll be ending my presentation by presenting you with a poll of how people that I know feel about global warming and its effects. Finally, I'll be considering the ethical implications of global warming and what effects can occur from counteracting and ignoring greenhouse gases. Firstly, I'll want to describe global warming in terms of physics. Although physics itself can be quite challenging at times, the theory found for global warming is much more simplified than other sections of the IB physics course that I had to undertake. In this section, I want to consider Sankey diagrams of fuel efficiency and an explanation of the greenhouse effect. To start off with though, I'd like to consider the different fuels available in today's world. You could probably name a few off the top of your head, but the main few that are always thrown around are coal, oil and gas. These are the big three, but I would like to go into a bit of detail about these fuels, starting with energy density. Energy density is a basic measurement of the chemical energy found within 1 kilogram of any substance, with energy measured in kilojoules. In this case, it's millijoules. It is obvious to see from the table that the substance which contains by far the most energy is uranium-235. This dwarfs the other energy sources in terms of energy density, with coal producing 2,360,000 times less energy per kilogram of the fuel. All the other fuels below coal have a similar energy density to that of coal. None can even begin to rival the amount of energy produced by uranium. Now, you as a reader may be thinking that we should be using uranium as our main energy source instead of coal and fuel and oil. And you'd probably be right in many regards, but I'm going to show you that the figure for the energy produced by uranium is skewed in more ways than one. Firstly, consider that the energy being produced is by uranium-235. Now, if you do not know what this means, I'll just explain in a little detail. When we describe uranium, it's important to understand that this is a very broad sense of the word, because uranium can actually be divided into a few categories, and these categories are different isotopes. The definition for an isotope is an atom which contains the same number of protons but a different number of neutrons. What this means in a physical sense is different isotopes have different physical properties, whether this be boiling point, density, or reactivity. Now you may be asking, well, what does this have to do with uranium? What's the problem? Well, the problem is that there is too much of one particular isotope and too little of another. Namely, there is too little of the isotope uranium-235 and too much of the uranium-238 isotope found naturally. In terms of percentages, there is about 97 to 98% of the uranium-238 isotope and only 2 to 3% of the uranium-235 isotope in any one block of uranium. This plays a very important role in the production of energy, as only uranium-235 is able to produce the energy needed. This means that when uranium is actually used in a reaction, much of it cannot actually react, as you're not getting pure uranium-235 isotope. However, there is a process that can be used to change the percentages of uranium-235 and uranium-238, and this process is fuel enrichment. This process is needed to produce energy from uranium, as a chain reaction is required to proceed so that uranium can be effectively used. I won't go into too much details about this chain reaction, but you can imagine it as a number of chains of dominoes. When one domino falls, it sets off a reaction and causes the next domino and then the next domino to fall, and so on. If there aren't enough of these dominoes and the space between them is too large, then you cannot get a chain reaction to occur. Consider the dominoes as uranium-235 and all the space in between as uranium-238. Increasing the amount of uranium-235 per unit area will of course mean that a chain reaction is more likely to occur. However, if this enrichment of uranium-235 is much higher than that of the fuel enrichment for an energy source, you can eventually obtain a nuclear warhead because so much energy is released. And that's obviously one of the problems of using uranium, as some of the waste as a byproduct of the fuel can be reused in nuclear warheads. Another problem with uranium is that there is not nearly as large an abundance of it than coal and oil. So that is another reason why the energy density does not exactly give 100% significance for the use of uranium. Next, for this slide, I want to talk about the inefficiency of using these different fuel sources and why you're never going to get 100% of the energy out of the fuel source. As you can see on the Sankey diagram, a minority of the energy actually put into a power station will come out as useful energy. The majority will become degraded energy, that is, energy that can no longer be used to provide work. What that means in a general sense is that you can't use this energy to power your car or to provide electricity to the home, and this can occur due to a change in the kinds of energy that the fuel exhibits. When you change the chemical energy of the fuel into potential or kinetic energy, you're going to have some of the energy given off as sound or heat energy. If the energy is used to move turbines, you're going to get some frictional energy from the particles interacting with the turbines. And then the turbines themselves moving around also produces friction. You're going to have this as a heat loss to the environment. This energy cannot be used anymore. Again, there will be a minor amount lost in the power station itself. No energy source is exempt from these inefficiencies, but the way in which fuels are converted to energy may be able to slightly alter how efficient the entire system is. Okay, now that we have finished with fuels and their inefficiencies, I'd like to talk about the greenhouse effect. The definition of the greenhouse effect is basically the trapping of solar radiation inside the Earth's atmosphere. But I'd like to elaborate a little on this by including a diagram and considering the particles involved in this trapping. The light that enters the Earth can be divided into different energy levels depending on their wavelength. The lower the wavelength, the higher the energy value. The radiation which causes most of the heating in our atmosphere is infrared radiation. It isn't visible by the human eye, but it's definitely there. So, when visible and shortwave infrared radiation enters the atmosphere, it causes the Earth's surface to warm up. This is known as albedo, as some of the heat is absorbed by the Earth and some is reflected in all directions. The absorbed heat, of course, leads to the higher temperatures. But what happens to the reflected light? Well, the Earth scatters this reflected infrared light with a higher wavelength in random directions. When this longer wavelength light is reflected back into the atmosphere, the greenhouse effect can occur. What happens is that some particles in the atmosphere absorb the higher wavelength infrared radiation and re-radiate it in random directions. This is due to resonance. That is, the particles are subject to a force that matches their own natural frequency and results in larger amplitudes of the infrared radiation. What this means is that infrared light is being reflected with higher energy levels than when it was absorbed by the particles. These particles that absorb and reflect the infrared radiation are carbon dioxide, water vapor, oxides of nitrogen, and a few more. When this infrared radiation is reflected, some of it goes back out into space, and some of it returns back to the ground and causes higher temperatures on the Earth's surface. Now, this process will repeat over and over and over again as the Earth reflects and absorbs this infrared radiation, and this is therefore shown as a trapping of the heat in the atmosphere. This is the role that greenhouse gases play in the atmosphere, in the sense of physics. But now I want to talk a bit more about the chemistry behind global warming. The first thing I would like to consider in terms of chemistry and in a broader sense is the particles responsible for much of the global warming that we experience today. I skimmed past a few of them on the last slide, but I want to go into more detail about the sources, as well as which ones contribute the most to global warming. On the graph, you can see some of the common sources of global warming, including CFCs, carbon dioxide, water, and oxides of nitrogen. From their relative effectiveness, on a scale in which carbon dioxide is 1, you can see that water vapor isn't very effective, while CFCs are extremely effective. The one which contributes the most global warming is carbon dioxide, naturally, and this is mostly due to the combustion in our car engines, where a substance combines with oxygen at extreme heats to form water and carbon dioxide. However, you can see that water vapor does not contribute to global warming, and that is because its atmospheric lifetime is extremely short. Nitrogen oxide is a lot more effective than carbon dioxide, but most of its sources are not man-made, and it does not contribute nearly as much to global warming. CFCs, on the other hand, are a very interesting substance, mostly due to how they react with the ozone layer, as well as their huge effectiveness as a contributor to global warming. Therefore, I'll mostly want to focus on CFCs in the next few slides, due to their nature and reactions in the atmosphere. CFCs stand for chlorofluorocarbons, and this molecule has a very negative effect on the Earth's atmosphere, namely, the depletion in the ozone layer. Over the last 30 years, it has been noticed that over much of the South Pole, there is a very large destruction of the ozone layer, equivalent to the size of the North American continent. Now, there is an importance to the ozone layer that I will discuss, and that is its effectiveness as a protector from high-energy light from the sun. This high-energy light is called UV light, and it can be very dangerous to humans and plants, as it causes skin cancer, eye cataracts, sunburns, and damage to plant growth as well as genetic mutations. The higher energy value also leads to a change in the world's climate as well. To understand the effects CFCs have in terms of chemistry, we must first look at the natural depletion and formation of ozone. In the stratosphere, when UV light hits oxygen gas, it causes splitting up of the molecule into two divided individual oxygen atoms. These oxygen atoms are extremely reactive and contain an unpaired electron, meaning that they want to find another molecule to bond with. Therefore, this oxygen atom will react with another gaseous oxygen molecule and will combine with it to form ozone, O3. This structure contains a double bond between the two oxygen atoms already in the molecule and a single bond between one of the oxygen atoms and the newly connected free radical oxygen atom. This structure is easier to break down than oxygen molecules, and therefore can be broken down when it absorbs longer wavelength ultraviolet light, to form an oxygen molecule and an oxygen free radical. So this is just basically the reverse of what happens to form ozone. These free radicals then react with more ozone to form oxygen gas, and hence there is an equilibrium between the depletion and formation of ozone. Now, how does this relate to CFCs? Well, a similar mechanism can be put forward to that between oxygen molecules. When the CFC reacts with ultraviolet light, it is broken up and one of the products formed is an ultra-reactive chlorine free radical. This free radical then reacts with ozone and forms oxygen gas and chlorate. This means that instead of ozone reacting with oxygen in a constant equilibrium, it reacts with chlorine instead to form more oxygen and less ozone. This means that there is now a disequilibrium and more oxygen gas is being formed than ozone. The decrease in concentration of ozone prevents it from shielding the Earth from ultraviolet light, which can then cause many of the problems discussed before. Now that we have considered global warming in terms of physics and chemistry, I'll turn my attention to a very popular area of debate among the global community in terms of climate change, and this topic is the ethics. When I consider ethics, I'm talking about the effects that changing our fuel sources may cause, and the effects that not changing our fuel sources may also cause. Firstly, I'd like to make reference to a poll that I conducted where I asked people the question, to what extent do you believe in global warming and its effects on the environment and us? From interviewing a small sample of friends, family and teachers, I've been able to find the following data when I've asked the sample this question. Now, from the data we can see that not everyone believes that global warming is having quite the effect that may be illustrated on the media or by politicians and scientists, as 12 people were skeptical of the effect that global warming has. 9 people believe that all the possible effects that global warming may have are definitely true, and finally only 2 people believe that climate change had no effect. This shows a general belief that global warming does have an effect on us and that conditions are worsening, but it was surprising to see so many people who were skeptical of the full effects that global warming may entail. In the next slide, I'll describe some of the reasons behind why we have not yet changed to cleaner energy sources. All the climate change figures may indicate to us that we need to change our energy sources and quickly. This may not be occurring at the rate which is expected of us to overcome global warming, and that is due to much of the negatives relating to switching from carbon dioxide inducing fuels to renewable energies such as nuclear energy, solar energy, and wind energy. Firstly, we have to understand that many of the largest corporations in the world are the oil and coal companies. Due to their immense power, not enough focus is being put on developing alternate fuel pathways, and the cheaper prices of many mainstream fuels prevent consumers from actually wanting to switch to renewable energies. Another problem is accessibility. Coal and oil are available day and night, but solar energy and wind energy are only available at different times of the day. And there are great fluctuations in the amount of energy produced per day and per season, due to the unpredictability of nature. However, nuclear energy is both a clean energy source in terms of no carbon dioxide, and is also available to power our Earth for hundreds of years. So what's the problem there? Well, the problem is the radioactivity of the uranium used in producing the energy, as it can also be used as a nuclear weapon, and the costs of nuclear meltdown are catastrophic. And this has occurred several times in the last 45 years or so. For this reason, many governments are now considering closing down nuclear power plants as they are too risky in their own regard. All these negatives together make it much easier for us as a society to just ease off and live with our current energy sources. But we also have to consider what will happen if we ignore alternate energy sources. Firstly, I will consider the most obvious pro that is associated with alternate energy sources, and that is that they are renewable. This means that their rate of production is much higher than their rate of usage. However, the amount of oil and coal that we can obtain will run out sooner rather than later, as our rate of usage is much higher than the rate of production. Another positive of energy sources, such as wind and solar energy, is that no toxic byproducts are formed as a result of their use, and that it does not affect the environment in a negative way. Many of these energy sources are free of charge, as the use of the sun's or the wind's energy cannot be paid to any one company or government. And finally, we need to use these alternate energy sources if we are to avoid increasing the greenhouse effect. Thank you for listening to my presentation. I hope that you enjoyed it and learned a bit more about global warming, not just in terms of the ethical implications, but also the science behind it, as without the science, we would never be able to understand global warming in the first place. I would also like to thank my family for collaborating with me on this project.